So now that we've talked about how to create a survey, let's talk about what to do with it now that you got the results. So you've asked people tons of questions, you have your results. How can you organize this data to make it look pretty? So we're going to talk about how to do some tables, and then later we'll talk about some graphs. First things first, the frequency distribution. So frequency distribution lists each category. These categories are called classes of the data and the number of occurrences for each category of data. We want to make sure that the sum of the frequencies, when you add them all up, it is the sample size. Right, it's the number of people you talk to in your sample. So if we look at this, right, problem number 1. So this is an example of a frequency distribution, right? These are what we call the classes, right? Each of these classes contain a certain number of people in them, right? Or a certain number of subjects, I should say. So in this case, we're talking about daily low temperatures. So what? Hopefully this is pretty explanatory, but what would this 4 mean in this class? What would this frequency mean? So hopefully you can see that this means that there were 4 days with lows between 55.0 and 59.9 degrees Fahrenheit, right? This 8 would mean that there were 8 days with lows between 70.0 and 74.9 degrees Fahrenheit, right? Hopefully that was easy peasy. So this first number right here, this is what we call the lower class limit. So it is the smaller of the 2 numbers that belong to different classes. Which means the upper class limit is going to be the larger of the 2 numbers. So if we look at example number 1, right? So if you notice, it says determine the lower class limits and the upper class limits. It also says class width, but we'll get to that later. So, what are the lower class limits? So we can see the lower class limits are 50.0, 55.0, 60.0, 65.0, and 70.0. So it's all of these. Remember, it's of each class, right? So this is the first one, second, third, fourth, all the way down. What are the upper class limits? Well, those are just the other numbers, right? So 54.9, 59.9, 64.9, 69.9, and 74.9. All right, hopefully not too hard yet. So the class width is what we call the difference. What does difference mean in math terms? Remember, difference means subtraction between consecutive lower class limits. What does consecutive mean? It's like one after the other, right? So it's consecutive lower class limits. That is super important. So if we look here, right? If we look at the class width, so between these 2 lower class limits, how many numbers are there? So we can do 55.0 minus 50.0 and we get 5.0. What about between these 2? Again, 60 minus 55 is 5. What about between these 2? 65 minus 60 is 5. 70 minus 65 is 5. What do you notice about this? The class width is always the same. Good, and that is always the case. This is kind of how we have our scale, right? It's using the class width. Now, what some people typically try to do is when they see class width, they think upper class minus lower class. So what some people would do was they would say 54.9 minus 50.0, right? The upper class minus the lower class, and get 4.9 as the class width. But this is not correct, right? The class width is between lower class limits. So some stupid thing that I like to think about, so if this isn't helpful, don't worry about it. But if we think about rectangles, right? If we think about a rectangle, typically we say that the longer side is called the length and the shorter side is called the width, right? So if you're doing 54.9 minus 50, you're kind of talking about the length of it, not the width of it, right? The width goes between the classes. So again, if that wasn't helpful, don't worry about it, but I like stupid things to help me remember things. So yeah, remember we're going between the classes. All right. So now that we know what to do, let's do it. So we know what a frequency distribution is. Let's construct some now. So the first thing you want to do is determine the first lower class limit. And make sure that it's at most the minimum value. Right? So you want to make sure that you're going to contain all of your data. So it could be the smallest number, it could be less than the smallest number. And then from there, determine a class width. So that will reach the number of classes being asked for. So it really could be anything. So let's start with this one, right? So problem number 2. Well, I guess we should talk about all of it. Yeah, we'll talk about the first 3 rules and then we'll move on to the example and kind of put them all together. So a good place to start is going to be the maximum value minus the minimum value divided by the total number of classes you want. And then number 3, determine the rest of the lower class. So the third one, you determine the rest of the lower class limits by adding the class width to each lower class limit until you've surpassed the maximum data value. And make sure you end with the correct number of classes. Okay. So now let's look at problem number 2. So let's put it all together. So a lot of words, let's explain what all of that means. So the following data consists of weights of 25-inch nails. So construct the frequency distribution with at least 5 classes. Okay, so step 1, we need to have a starting lower class limit. And then step 2 is to have a class width. Now, there are a lot of different options. And actually, if we were in a classroom, I would say everybody just go for it. Try to figure out a different one for yourself. And we would end up seeing that lots of people would have different answers. And that's completely okay. But there are certain answers that would not be correct, right? So for instance, we need at least 5 classes. So if we had a starting lower class limit, so first of all, we need to see what is our smallest number. So smallest number, maybe it's the 1.324, 2724. Yeah, okay, so that one's the smallest. So we could start with 1.324. That'd be fine. And then the class width. So there is basically, you don't want a too big a class width or too small a class width. So for instance, if we had the class width as 1, right? So we would have our length in inches and then frequency. So step 3, it's super important. Everyone forgets this. So remember, you are going down. You write your first class width, and then you go down, adding the class or lower class limit, and then you add the class width going down. We're finding all the lower class limits first. Don't try to go back and forth. You're gonna mess yourself up. Don't try to find the upper class limit first. Just find all the lower class limits first. I promise this. Everyone messes this up because they try to do 2 things at once. Just go all the way down first. So if we had a class width of 1, right? So 2.324, 3.324, 4.324, 5.324. But if you notice, right, where are all of our data going to be? All of this data is in the ones, right? Which means that all 25 are going to be in this one class. Everything else is going to be 0. So in actuality, we only have 1 class because all the ones after that is 0. So this is not a good one, right? We don't want 1 class to have all of the data. That doesn't tell us anything. We also don't want to have 25 different classes, right? Or even more. So you don't want something where you're only going to have 1 class, and you don't want something where you're going to have something super small. So we could have 0.001, right? So if you notice for that one, we're going to have 1.324, 1.325 because we're going down adding, 1.326, 1.327. And if you notice, this is going to take forever. We're going to have way more than 5 classes. We're going to have one for every single one of these basically, and even more than that. So that also is not something that we want, right? We don't want only 1 class. And we don't want each of the values to have their own class. So apart from that, you just do whatever. So some of us can just, we can just kind of do whatever we want. So again, remember, I said a good place to start for the class width is doing the maximum value minus the minimum value, divide by the number that you want. So in this case, we want 5, right? At least 5 classes. At least means you can have more than 5, right? So if you end up with 6 or 7, that's totally okay, but you need to have at least 5. So the maximum value here we can see is probably this number, right? So 1.368 minus 1.324 divided by 5. If we type that into a calculator, we'll see we get about 1.0088, right? So again, we can just round it. It super doesn't matter. So I'm just going to round this to 0.010 because this is all about an estimation anyway. So I'm just going to say a class of 0.010. Now remember, the next step is we go down. So 1.334, 1.344, 1.354, 1.364, 1.374, right? And at what point do we stop? Remember we said our biggest number is 1.368. So is there going to be any of them in the 1.374? No, there will not be, right? So do we have 5? 1, 2, 3, 4, 5. Perfect. Now remember, this is one way to do it. We could have done it another way, right? We could, so remember, the starting class limit doesn't have to be the actual minimum. It can be, but if we want to make it simpler on us, we could just put a 0, right? Counting up by 10s is going to be way easier than counting up by 4s, or having those 4s there. So we could also just add everything up in the teens. It's going to be a little easier counting things later on too. Again, you can do it many ways. All these results will vary, but this is what I found to be kind of the easiest thing. Just kind of starting at 0, wherever that 0 is, and then going up by 10s or 5s or something like that. Making sure you have at least the number of classes that they want. All right, so remember, step 3, you go down to find all the lower class limits. Step 4, you want to determine all the upper class limits. So, making sure that we note the same number of decimals as in the data, as the data need to include all possible points. So basically, if you do have 1.320, you should actually include the 0, right? If there are 3 decimals in your data, there should be 3 decimals in your table, right? If there's 2 decimals in your data, you need to have 2 decimals in your table, and here's why. A good way to determine the first upper class limit is to subtract the smallest decimal from the next lower class limit. Oh, well, subtract 1 decimal from the next lower class limit's smallest decimal place. And then after that, we can just add the class width to it, to each of the upper class limits. So here's the example. So what number comes before 1.330? Hopefully you can see it's 1.329, right? What number comes before 1.340? 1.339. And if you notice, right, how do we get from here to here? We just added the class width. So the next one would be 1.349, 1.359, 1.369, so on and so forth, right? Now, if you didn't have these zeros, right, you might instead write this, right? What number is before 1.33? 1.32, right? But essentially, right, 1.32 and 1.32, that's just the same number, 1.320. So if this number is 1.330 and the highest number in this can be 1.320, where would, for instance, 1.324 go? It can't go in the second one because 330 is the smallest, but it can't go in the first one because 320 is the biggest, right? So this number has nowhere to go. So that's why you always need to have, right? You need to have, if there's 3 decimals in the data, you need 3 decimals in your table. And that way you will know that this answer is actually a 9, not a 0. Good. Five nine 1.369. So like we said, first thing you want to do is find all your lower class limits. Then you want to find your upper class limits. What people always do is they add across and then they get messed up. All right? Make sure you do your lower class limits first, then do your upper class limits. Don't try to do both at the same time. You will get it wrong. All right, and then the last thing you got to do is just figure out what the frequency is. So take each individual data value and put a tally mark in the appropriate class, and then add them all up to get your frequency. So this one literally is just counting. So let's just count. How many are in the 20s? And see, if you do it this way with 20 to 29, so if you did it the other way, you would see that it'd be 1.24 and 1.333, right? And you can absolutely do it this way, right? Because the next one will be 1.334, 1.343, and this is totally okay. It's just going to be a little harder to count, right? Some of them are in the 20s, some of them are in the 30s, but if you do it this way, it just makes things a little easier, right? Because now all I have to do is just look and see which one is in the 20s. So 24, 24, 27, right? So 3, and I would just write the number 3. Good, and then you would just keep counting. So how many are in the 30s? There's 1, 2, 3. So looks like another 3. How many are in the 40s? 1, 2, 3, 4, 5, 6, 7, 8, 9. I think that's it. Now, you don't have to do the tally marks if you don't want to. That's totally okay. All I need to do is see the numbers. Let's look at the 50s. So 1, 2, 3, 4, 5, 6, 7, 8. I think that's it. And then how many 60s do we got? 1, 2. All right. So maybe this is it. What's a good way to double check ourselves? So remember, if you add up the frequencies, what should you get? You should get the total number of people, right? The sample size. So do we? Let's add them up. What do we get? Yeah, we get 25, right? So that's probably correct. We probably did it correctly. All right, so this would be our frequency distribution. All right, let's do another one. And so again, your results can vary. They might be different than mine. That's totally okay. So the following data illustrates the number of customers at a restaurant for 20 days. So construct a frequency distribution. So remember, first thing we need is a starting lower class limit and a class width. So I have, we see that 2 is the smallest number. So I just need, we can use 2. We can also use something else. I might actually suggest that you do your own and just see if it works. Because you don't have to do the same thing as mine. These results very well will vary. Very well will vary. Yep, I just said that. So we just need something at least, at most 2, right? So we could start with 2. We could also start something smaller than 2. So I think 0 is probably the easier one to start with. And so 10 is always a good number, right? So let's do 10. So we got number of customers and frequency. All right, so start with 0, 10, 20, 30. We need 6 classes, 40, 50, 60. Oh, we only need the 60, only 50. Yeah, 1, 2, 3, 4, 5, 6. There we go. So what's the biggest number that we got? It looks like it is 46. So is anything going to be in this one? No, it will not, right? So in actuality, we would end up with 5 classes. Not great. So can we use 10 as our class width? No, right? We need something smaller. Well, let's do the... So since 10 didn't work, let's just look and see what the suggestion was, right? Remember, it was maximum minus minimum divided by the total number they want, which is 6. So we said the biggest number was 46, smallest number was 2. So when we divide that out, we get about 7.3. So let's just round up to 8. Again, doesn't matter. 7 might work. 8 could work. We're just kind of doing a trial and error type thing. This is a good place to start. So, again, we are only looking at the lower class limits. We are not looking at the upper class limits. Do not do both of these at the same time. So, the first one was 0. Let's go up 8. So, we have 8, 16, add 8 again, 24, add 8 again, 32, 40. All right, that's 6. Let's go up one more just to make sure. 48. All right, would anything be higher than 48? 48 or higher? No, remember we said that 46 was the highest. Okay, so there's not going to be any in here. which means that we do have 1, 2, 3, 4, 5, 6 classes. All right, so now we got to figure out what is the upper class limit. So remember, you just subtract 1 from it. So what's before 8? 7. And remember, since these don't have any decimals, our data shouldn't have any decimals either. What comes before 16? 15. So we can either do it that way, or we can start adding by 8s, right? So if you add 8, you get 23. Add 8 again, 31. Add 8 again, 39. 8 again, 47. Good. So now we just got to count them up, right? So how many are between 0 and 7? So we can see there's 2. There's 5. So it looks like 2 are between these two numbers. Between 8 and 15. So we got 9, 11, 14, 14, 15. So looks like that. So 5 numbers. So again, right, it's not as pretty, but we can do it. You also could have gone up by 5s, right? You would have had more than 6, but that's okay. 16 and 23. So we got 16, 18, 17, 16, 23. So another 5. All right, we got 24 to 31. So 26, 26, 26. Looks like those are it. Between 32 and 39, so all the rest of the 30s. So 34, 36, 37. All right. And then we go between 40 and 47. So we got 46, 45. How can we double check to make sure they're right? Add them up. What should we get if we add these up? We should get 20, right? Because that's the number. Do we? Yeah. We get 20. Good. So this is what our frequency distribution will look like. Okay, so now just to reiterate, because again, you might have a different graph than I do. So as long as your first number is not 0 and your last number is not 0, you probably will have a correct frequency distribution. The insides can be 0, right? That tells us stuff. That tells us that the data just doesn't have any numbers in that value. But as long as the first class is not 0 and the last class is not 0, any other number inside can be 0. That's okay. That's completely okay. Yeah, so if you end up, doing 5s, for instance, or something like that, and you end up with a 0 inside here, don't think you did it incorrectly. You absolutely could have done it correctly, right? Just the first number and the last number can't be 0. Because otherwise you could just take that one out, right? If the first one's 0, then we don't need that class. Because you can keep going, right? We can keep going and having the next one is 0, 0, 0. It just goes on forever, right? But that's not going to be telling us anything. That's not helpful. All right. So we have constructed frequency distributions. Let's talk about relative frequency distributions. So a relative frequency distribution is the proportion, or percent, so proportion is just a fancy word for percent, of observations within a category, and is found using the probability formula. So remember, probability is just the number in your event divided by the total. So simple probability. A relative frequency distribution lists out each category of data together with the relative frequency. And the sum of the frequencies should be what? So if you have them all in proportions, so in decimals, right, or percentages, if you add up all the percentages, what should we get? So we should get 100%, right? Remember, proportion is just a fancy word for the decimal form. So if those were in decimal form, how much would, when we add them up, what should they be? It should just be 1, right? 1 is the decimal form of 100%. All right, so if we go back to problem number 3, so using the frequency distribution that you did in part A, let's make a relative frequency distribution. So again, yours might be different than mine, and that's completely okay, right? So basically, instead of these numbers, right, the frequency, we want to know what percentage. So we don't want to know how many people were or how many customers were in it. We want to know what percentage of customers were there. So number of customers. We still got 0 to 7, 8 to 15, 16 to 23, 24 to 31, 32 to 39, 40 to 47. But this time we have relative frequency. So we're just going to make it, as a general rule, probably, again, decimal form is going to be what we use in this class. So what percentage of people, what percentage of days had customers between 0 and 7, right? Well, we know there's 2 days that had that out of how many? Remember, if you add these up, it would be 20. So 2 out of 20. And we divide that out, we get 0.10. So this number is 0.10. So there were 5 days between 8 and 15. What percentages is that going to be? Again, you do 5 divided by 20, and you get 0.25. So 25%. And if you notice, that's just what we're doing. So hopefully this isn't hard, right? We're just finding the percentages. So we just divide by 20, divide by 20. All right, we already get 0.25. When we divide the 3 by 20, we get 0.15. We already did 3 divided by 20 to get 0.15. And then 2 divided by 20 to get 0.10. So again, if you have a different frequency distribution, that's okay. You will end up with different numbers. But when we add up all these frequencies, what should we get? So we should get 1. And then do we? Yeah. So here is our relative frequency distribution. All right, hopefully it wasn't too hard. So let's talk about cumulative frequency. So a cumulative frequency distribution displays the combination frequency of the category. So in other words, it displays the total number of observations less than or equal to the upper class limit of the class. And then the last class should contain the sample size. So let's think about this word, cumulative, right? What does cumulative mean? So for instance, at the end of the semester, if we had a cumulative final exam, what would that mean? It means that the day of the exam and everything before it is going to be included, right? All of the things are going to be included from that day to the first day of class. Well, that's kind of the same thing here, right? Cumulative means the same thing. Whenever we stop, we want that number and everything before it. So let's look at some examples. So for problem number 2, let's construct a cumulative frequency with this given data. All right, so everything else will still be the same. We'll have 1.320 to 1.329, 1.330 to 1.339, 1.340 to 1.349, 1.350 to 1.359, and then 1.360, 1.369. All right, so what we do is we look at the upper class limit, and we say how many numbers are lower, right, or at most 1.329. So how many from this graph, I mean, you can actually count out too, but how many from this graph are no more than 1.329? Hopefully you can see it's these three, right? These three are between 1.320, 1.329. So there's 3 numbers that are less than or equal to 1.329. All right. What about 1.339? How many numbers are less than that? So it's not just these three, right? Because these three definitely are. Right? These are in the 30s, but wouldn't all the 20s be less than 39 as well? Right? Wouldn't 1.324 be less than 1.339? Yeah. So there's where the cumulative part comes in. So it's not just these three, but it's these three plus these three. So it's 6. And then if we have 1.349, how many are less than or equal to that number? Well, it's these 9. But again, these 3 in the 30s are going to be less than 49. And these 3 in the 20s are going to be less than 49. So 3 plus 3 is 6, plus 9 is 15. There are 15 numbers. Hopefully you're starting to see the pattern, right? How many are less than or equal to 15.9? Well, we just add the 8 to it, right? So 8 plus 15 is 23. And then the last one, right? How many are less than 1.369? Well, all of them are, right? We said that the highest number was 1.368, so all 25 would be. And then 2 plus 23, or when you add them all up, we get 25. So in this case, right, it's not when you add them all up they're going to get you stuff. It's the last class will get you stuff, right? The last class should be the total number for a cumulative frequency. All right. Let's talk about cumulative relative frequency. So the relative frequency is, this is basically exactly what you might think it is, right? So it displays the proportion or percentage of observations less than or equal to the upper class limit. And again, the last class should be either 1 or 100%. So this is the exact same thing. This is just using the relative frequency. So problem 3, part C. Let's use our relative frequency from part B and make a cumulative frequency distribution. So again, we got number of customers, and we got frequency, and by that I mean cumulative relative frequency. All right, so you got 0 to 7, 8 to 15, 16 to 23, 24 to 31, 32 to 39, 40 to 47. All right, so again, how many are going to be less than the 7? We see it's just 0.10, less than or equal to. For this 15, right, we have the 25% and the 10%, so I need to add both of those together. So 0.35. Less than or equal to the 23, well, now we have to add another 25 to that, right? So 25 plus 25 plus 10 is going to be 0.60. Then we keep going. So another 15% is going to be 0.75. Another 15% is going to be 0.90. And then another 10% is going to be 1. Which is exactly what we wanted, right? Remember, the last class should be 1. So we got our cumulative relative frequency distribution. All right. Now let's talk about shapes of distributions. So there are 4 that we're going to talk about. The first one is a normal distribution. So this is a bell-shaped curve. So a bell shape looks like this, right? So there's 2 parts of this definition. So it starts low, goes high, and then goes back low again. So low, high, low is going to be one part of the definition. And then what's going to be the second part of the definition? So this is what a bell looks like. So is this a bell? No, right? So what else does this bell need to have? Because this is low, high, low, but this isn't a bell shape, right? It'd be a really weird bell. So it also needs to be symmetrical. So when I ask in the future, what's a normal shape, normal bell curve, right? It's going to be low, high, low, and symmetrical. Uniform. Uniform has the data that is evenly spread or evenly distributed over all the values. So essentially, it's just going to more or less look like this, right? Just straight across. So the way I think about it is uniform. Soldiers wear uniforms, right? And soldiers march in lines, right? So everybody's at the same length. Again, something stupid to think about. But if it helps, hey, go for it. All right, so a right skewed or skewed right distribution is going to have a longer right tail. A left skewed distribution is going to have a longer left tail. So it's where the tail is. It's where all the data is getting pulled. So a right skewed is going to look like this, right? Where that tail is on the right side. A left skewed distribution is going to be the opposite, right? So kind of what we drew earlier, that was a left skewed. All the stuff's on the left side. So we can actually talk about this with all types of different things, right? So if we go back and look at our distribution, right? Let's look at our cumulative frequency distribution. So what kind would this be? Well, if you notice, right? So if we kind of thought about this, it's going from 10%. So if we kind of drew this on a line, right? It goes 10%, 35, 36, or sorry, 35, 60, 75, 90, 100. So it kind of looked like this, right? What kind of, if you had to choose one of the four, what would this be? Well, definitely wouldn't be uniform, right? It's not all the same. It definitely wouldn't be normal. Doesn't go up and back down. So what would it be? Well, notice the lower side is on the left. So this could be a skewed left or a left skewed. Right? We would see the same thing with any cumulative, right? It's going to just keep going up. So once again, this would also be a left skewed or a skewed left if we talked about that. All right. What about our actual frequency distribution for problem number 2? So yeah, so what would this be? Well, you can see that it starts at 3, 3, 9, 8, and 2, right? So if we had heights, it kind of looks like this. So maybe normal, right? It could be normal, low, high, low. But if you notice, there's more highs on the right side than the left side, so maybe it's a left skewed, right? It's not exactly symmetrical. What about this one, problem number 3, the relative with the frequency distribution? So we can see that it would be 2, 5, 5, 3, 3, 2. So this looks like it could be a right skewed, right? Seems like the graph is high on the left and then low on the right. Also, this could be uniform. So I know you're thinking, well, no, hold on a second. Uniform's supposed to be all the same. But 2, 3, and 5, these are all pretty close to the same numbers. We're not going to get the exact same, right? But if we zoomed out, if we were looking at a graph that went from like 0 to 50, all these numbers are going to be about the same, right? There's not going to be too much of a difference between these. So this also may be considered uniform. Just depending on how you look at it. Cool, cool, cool. All right, let's talk about some bar graphs. So this will be the last part of this video, just the bar graphs. All right, so bar graph We typically know what this is, right? It's either going to be a horizontal or vertical bar graph. So rectangles of equal length are drawn for each category. We want to make sure that the rectangle's category, the height of the rectangle represents the category's frequency or relative frequency. Right? So that's kind of what we were doing earlier, if you noticed. Right, we were saying, so when we had the 1, we had 2, 5, 5, 3, 3, and 2, right? Remember the one that we had just graphed earlier? That's essentially what we were doing. We're making a bar graph with it. We just didn't actually write down the bars. The heights were their frequencies. All right, so first thing we got to talk about is a Pareto chart. So Pareto chart's super easy. It's a bar. It's a graph whose bars are in decreasing order. So would this be a Pareto chart? No, right? Pretty easily. This is not a Pareto chart. Why? Because it's increasing. Right? That's a no-go. All right, what about this one? Is that a Pareto chart? Nope. Because it's decreasing and increasing. No go. All right, what about this one? Part C. Is that a Pareto chart? Yeah. Right? Because they're all decreasing. Good. Pretty easy, hopefully. Also, what kind of distribution would this be of those 4? If we had to pick one of them, would it be normal, uniform, right skewed, left skewed? Well, since it's being dragged to the left side or to the right side, right? Most of the data is here and it's getting dragged down to the right. This would be right skewed or skewed right. Good. So all Pareto charts, more or less, are going to be right skewed. All right. Last thing, and then we're going to be done with this video. There'll be another video to continue this lesson. So a histogram is constructed by drawing rectangles for each class of data. The width of each one is going to represent the class. And the height, we already said, is going to represent the frequency. The biggest thing with histograms, super important, the rectangles must touch each other. For histograms, they have to touch each other. And the reason why is because if they don't touch each other, that has to tell us something. So for instance, if you have a graph where everything is touching, and then there's a skip where all of a sudden something is not touching, right? Well, this tells you something, right? If all of them do touch, that means that there was no data, there was no frequency in this one. And that's helpful, because if they're touching, we can easily see, oh, there was nobody in this class. However, if it's something like this, so this is good, this is not good, right? If they're separated, well, it's hard to tell, right? This one looks like it has less space than this one. So did someone just draw it incorrectly? Should there be a bar graph here? Should there be a bar there? It's hard to tell, right? So this is not the way to do it. If you have everything touching, then the second one bar doesn't touch. That means that there is no frequency. So for histograms, they have to touch. All right, so problem number 4. 2 more problems and then we are done with this video. Yay! So, how many people are in this study? How can you figure out how many people are in the study? Well, remember, the heights are going to be the frequencies, right? So these heights tell you how many people are there. So there's 2, 3, 5, 2, 1, and 2. So if we add up all these numbers, we end up with 15, right? So there are 15 people in the study. How many people had cholesterol between 36 and 71? So 36 is right here, and 71 is right here. So how many people are between these two numbers? So 3 plus 5 plus 2 plus 1, we get 11 people. What class or classes had a frequency of 3? Oh. So if you notice, the frequency of 3, that was the class from 36 to 44. Part D. What class or classes had a frequency of 2? So we had a class of 2 right here at 27 to 35. We had a class of 2 here at 54 to 62. And we had a class of 2 right here at 72 to 80. So we had 3 different classes. All right. So, last question. Class, what's the class width? So, class width, so some people might say that that would be 35 minus 27, remember? So 35 minus 27, and we get 8. However, what was the definition of class width? It's not between the classes, within the classes, right? It's between different classes. So a class width is going to be 36 minus 27, which is 9. The class width in this case would be 9, not 8. Yeah, super easy to mess up. Last problem. All right, so for this histogram, how many people are in it? For this histogram, how many people are in this study? So it says a range of 25. So that's how we know, right? There's 25 people in this study. So we couldn't count this time because this is a relative frequency histogram, right? This is relative frequency. So this just tells us the percentage of people. All right, for this histogram, what's the class width? So hopefully you remember that's going to be between 2 different bar graphs, right? So that's going to be 26 minus 1, which is 25. So for this histogram, what proportion of people were between 1 and 50? So here's 1, here's 50, so we got to look at these 2 bar graphs. So it doesn't tell us exactly, so we just got to, kind of have to guess. So this could be about 16%, right? 0.16. This could be about 31, maybe. So if we add 0.16 and 0.31, we get 0.74. So part D for this histogram, what class or classes had a relative frequency of 0.15? So we can see that this definitely is not 0.15, right? It's a little over 0.15. So the only one that has 0.15 in this histogram is 76 to 100. All right, now some of y'all might have been screaming at me this whole time, which is great. I hope you were. Because part E, which you don't have on your chart, is this a histogram? AKA, should we have been answering these questions to begin with? No, it's not, right? Why? Why is it not a histogram? Because there are gaps. Good. So if every time if I was saying for this histogram and you're like, no, it's not a histogram, you were absolutely correct. We should not have done any of these problems. But good practice anyway. All right. If you have any questions, let me know. If you have different histograms or different, if you have different frequency distributions earlier on and you just want to text them to me or email them to me to let me see if, if they're correct, if you don't feel comfortable, I would love to look at yours and let you know if you're right or not. But otherwise, y'all have a great day.